So I want to prove this. I could have just left this as an exercise, but I think there's kind of a fun thing in there. It's another sort of way to think about, another kind of application of someone's limit in it. What I'm gonna first do is find a maximal chain of primes. And, and this, as you might guess, will apply to Zorn. Okay. So, okay, so let's think about what is a maximal chain, or what is a chain of primes? Such that, all this. CI, a chain of primes. And each,
chains on inclusion.
That's what I was gonna ask, actually. So here's what we have. We have this collection of chain of primes. Let me first note that this is, in fact, so there's a chain of primes between P and Q. Actually, there's a smaller one, right? Because I could just have, technically, I could have just the chain P, but the chain Q by itself, but there's more dramatic ones, say I actually use two. Right. So, yes, so this brings me exactly to your point. This needs to be partially reset. So how do we order this? So let's say C is less than or equal to C prime.
Every element in the chain C is in the chain C prime.
Good, I think that's what you're gonna do. C is less than, via C is less than or equal to C prime if for all PI in C, PI is in. So that means whatever primes you use in this chain, you're using at least this many here, right? Let's kind of go through it and convince ourselves. Notice that any chain is less than or equal to itself, right? And two, right? Then every prime here lives in here. And if you're a prime that lives here, you live in here. So every prime that lives here, and so you get this. Right? And let's see what's the anti-symmetry free. Well, what you're saying here is every prime that lives in this chain lives here, but if you're a prime that lives in this chain, lives here, so it has to consist of exactly the same collection of primes. Right?
So why can't we just use set theoretic conclusion? Isn't this just the same thing?
Well, because this is so it's set theoretic conclusion. So we're saying that C is less than, yeah, I guess that's what you're saying, because what you have is a set of prime ideals here, right? But by the way, what do you suppose it means to be a maximal chain? right, we would come to that.
A chain where you cannot put any more elements in the chain.
Right, um, let me word this differently. So a chain C is maximal if,
You have a prime ideal outside the chain, that prime ideal cannot be comparable with every element in the chain.
okay, right, I'll say something equivalent. Such a chain is maximal if given P, given any prime ideal let's say, P hat, such that it can be wedged between P and Q, given any prime ideal, and such that P hat is comparable to all elements of C, then P hat is in C. Do I really need this condition?
Yeah.
Did you do what, how come?
Being done.
Right, because you might have a prime that's, for example, bigger than Q, and it's still comparable to everything in here, but you don't want to include it because it's outside of our range, right? So, right, if it's a domain. So we now have our partially ordered set, right? And we have a way to compare these chains. So now what I want to do is to apply Zorn, we need to show every chain in gamma as an up. Right, so now we've got a chain of chains, right? I feel like Aretha Franklin up here, right? So what do we do here? So let's let chain of, say, chains of primes. It's the usual, isn't it? Okay, the first thing I want to do is notice that we only need to guarantee that this is in fact a chain of primes. Well, so you, so let's let P alpha beta and then U. Right? So there exists, this union, so I do this for emphasis, all the chains. So there exists, I in the index set such that, well, let's say, I such that, P alpha is in the I chain and P beta is in the J chain. But again, these chains, this is a chain of chains, so they're comparable. Without loss of generality, say that Ci is Ck, therefore Ck, right? And so, again, without loss of generality, P alpha is contained in P beta. So, and of course, this is, so U is a chain of bonds. Between P and Q, because of course both P alpha and P beta are. Everybody okay with this? So U is actually a big fat chain of primes. And it's clearly, comparable, it contains every element of the chain, of these chains of primes. So by Zorn, there exists a maximal chain of primes. In this sense of the word, right? So if you have any other prime that's between P and Q and you can compare it to this maximal chain, then that prime already had to live in the chain, right? Let me also point out as a word of caution, with most examples that you would probably first come up with if you were thinking about it, there's not many chains between P alpha and P beta, right? If you look at a PID or something like this, or either that or the chains are fairly simple to understand. Notice that, the maximal chains, there might be a lot of them. Let me give you a quick example. Actually, let me keep this where we're going, then I can give you an example in a moment. Okay, okay, so now, what we have is a maximal chain. Um, let me emphasize this. Let's see, let's just pick some maximal chain. There might be many to pick from. And let X be in Q minus P. In the setup of the theorem, I did say that, that Q strictly contains, P. So let's let P1 P alpha is in chain and, X not in P alpha. So what do? I'm gonna look at everything in this big fat chain, and I'm gonna select all the prime ideals that do not contain this X. That's, not in Q, and I'll let P one be the union of this, right? On the other hand,
Intersection.
that's right. Intersection. All the primes in the chain such that X is in. Notice that, P1, notice that X, is not in P1, but is in P2, so these are distinct. Notice that. That's certainly true. Notice that Q1 contains Q, that must be true. And notice that I sort of get this in the sense that X lives here, but not here. But how do I know that these are comparable? That's right, because it comes from the chain, right? So this is, in a certain sense, everything in every one of these P alphas is comparable to this, right? Because this whole thing is a chain. So given one of these P alphas and one of these P alphas, you have to be able to compare them, right? No way does this one contain this one, right? Because no X, yes X. So these animals all have to be bigger than all these animals, and that's why you can contain them. Everybody okay with that? And the strictness comes from the fact that X lives here, but not here. Okay. Now, the last thing I guess that we have to do is show that there's no prime between there. See that there is no prime strictly between them, P1 and Q1. Let's note that note that if such a prime A exists, then A is comparable. If there's a prime that lives between here and here, then it's comparable to all elements of the chain, right? So A is in the chain because of maximality. And so now you just break it down into cases. So if X is in A, then A contains Q1, and if X is not in A, then A is contained P1. Right? So you can't squeeze anything in between. So this is often referred to as the next neighbor's property. And as we discussed last time, if you have a partially ordered set that can represent the prime ideals of some integral domain or any community variant identity, then it has to have that property, this next neighbor's property. Let me give you kind of a quick example just for fun. Okay, can somebody give me, a maximal chain in here? Of prime ideals. Oh, you missed your golden opportunity. There's one. There's actually infinitely many maximal ideals in this ring, right? But I'm gonna pick one that's easy for my pea-sized little frame. Now, this is a chain. Is it maximal? Can anybody think of something else that we can slide in between?
X or Y.
Okay, right. Point. As it turns out, so this is a statement without proof, we might get to this later. This is a maximal chain because this ring is what we call two-dimensional, right? So, it turns out that, and in fact, you can sort of see this because, if you modify this right here, you get the field. So this is a maximal ideal, and this quotient here over this ideal. Anyway, so this, you can sort of argue this maximal, and as you point out, favor of Boston fits. So there's two maximal chains right here, right? Because these two aren't comparable, but they're certainly, it could be the middle length of lane. Is that it?
Irreducible polynomials.
I can just start going crazy, right? And in fact, there's infinitely many. There's infinitely many of these maximal chains, right? In fact, there's an interesting theorem that I hope to come to, that if, so I'll do this here. Tell me if you've heard this theorem before. If you have a Noetherian ring and you have a prime ideal and another prime ideal, if there is a prime ideal in between these two, there's infinitely many. Right? So if you have a Noetherian ring, so if all ideals are finitely generated, if you have two primes and you can find a new one in between there, there's infinitely many.
So a corollary of Pearl's height theorem, right?
If your ring is not Noetherian, this is not necessarily so. In fact, you can have linearly ordered stacks of primes, which is strange. I'll show you that. There's a nice segue because we're going to talk about valuation domains in a bit. But in a valuation domain, you can actually build stacks of primes like a stalk, just like that, and there's no others. For an Noetherian ring, you can't ever do this. Well, unless your stalks are really, really small, right? Like 0 to maximal. Okay, I am going to talk briefly about localizations. I've covered sort of most of the generalities actually in the homework. Let's just, and I'm gonna say something more general than I did in my notes. I don't know why I was so lazy. Let's recall first, for a domain, R. So I am gonna start this off before I write something down formal. How many of y'all have seen localizations or fractions in some? For domain R, and multiplicative set S in R, and you can default this to not contain 0, because what happens if your set contains 0 is the localization becomes a 0 ring. Then RS, we think of this as fractions. with addition given this way. Two. With R prime and R, S prime and S. Right, so this is a way of sort of making fractions. For example, this is a terribly important example. If S is R minus 0, then this is in fact a field. It's the set of all fractions where you can take any denominator you want as long as it's not 0. And this is called the quotient field R. In this notation, when R is a set, then R over S. And remember, these fractions are equivalence classes, right? And we're going to talk about that in a moment, like 1/2, 2/4, 3/6. These are all the same thing. It's really classes. All right. Yeah. P and R prime and S is R minus P. What do we know about S? Well, S is now the set complement of prime ideal, right? It's not just any random multiplicative set, it's a very nice one. It's saturated, it's multiplicatively closed, right? Then so I should make apologies for community of algebras everywhere because these notations are, it's confusing. When RS, this is the set of, in fact, I'll write it that way. Just like before, R over S, where S is in S, R is in R. This is sometimes written this way when P is a prime ideal. This is the set of R over S, where R is in R and S is not in P. Right, because the multiplicative set is not that, I mean, after all, think of it this way, 0 is in P, you don't want to divide by 0, do you, right? So this is everything, this is called a localization at the prime ideal P. And we'll talk a little bit about this, but when you see this notation and this is a set, that means these are the denominators. When you see it and it's prime ideal, that means it's everything that's not, the denominators are not this, right? Notice that the quotient field is R localized at 0, right? Because the, this is certainly an ideal and the denominators are everything that are not 0, right? Here's so for example, let R be Z and let P be 5Z, the same. Then in this case, R localized P, localize that 5Z. This is the set of fractions of the form N over M, where GCD of 5 and M 1. So I just want my denominators to not be divisible by 5. Right?
And we want, and then be right, right? Co-prime.
What's that?
And we want N and M be equal primes, right? Because, you know, for example, we have 5 or 10 in the thing.
But it didn't have to be, right? It's certainly, because, if N and M are co-prime, that means they've got a factor in common, which of course wouldn't be 5. But that's just in the same equivalence class, right? I mean, you can certainly reduce the fraction, right? More generally, let me give you a definition. So I like to start out this way because here's what happens, right? Localizations, they're just kind of fractions or like maybe pieces. This one right here, this last one is a piece of the rational numbers, right? I don't have, for example, 1/5 in this last string, but I've got pretty much every other denominator that I want, right? But this does certainly stimulate the question, okay, what happens if you got 0 divisors, right? Because certainly, and in fact, I haven't really dealt with this well here, so not about how to deal with it. The problem is, of course, given our rules for adding fractions, if I add fractions or if I multiply fractions, the new fraction created by adding or multiplying has a denominator that's the product of the other denominators, right? The original ones. So what if the product of those two happen to be 0 or something like that? So let me give you the following. That's definitely let R be a commutative ring with 1 and S in R a multiplicative equivalent set. Now, the first thing I'm going to do is I'm going to define an equivalence relation on an equivalence relation on okay, so I'm gonna take the Cartesian product of R and S, I'm gonna find an equivalence relation this way. So I am going to declare two of these to be equivalent if there exists some perhaps third party in S, such that S times RS prime minus R prime S times S double prime is 0. I'm gonna, now, look, you guys gotta slog through this in homework, and my apologies. But, it's not completely clear, is it, that this is an equivalence relation, right? I mean, I guess like, symmetry probably is, and so, and something's equivalent to itself, but transitivity is not clear. In the sequel, I'm going to just like the domains, I am going to write the ordered pair or its equivalence class, I should say. Right, let's do the equivalence class. The equivalence class of RS, I'm gonna write as a fraction, right? Just like I did with the ordinary. Then RS, which is the set of equivalence classes, R and R, S and S. If you look at this collection of equivalence classes, so you take the equivalence relation, you group this and use that to group these into equivalence classes. This set of equivalence classes becomes a ring under with operations given by one, same as we had before. Two, and this ring is called the localization of R at set S. Now, I brought this up a couple of times before, so now I'm dying to get to the bottom of this. So what happens if 0 is in our multiplicative set? That is right. If 0 is in S, then this relation right here implies that any two equivalence classes are the same, because all you have to do is take S double prime and 0. So when I build my ring, assuming that you believe me here, when I build my ring, I have a ring with only one element. So it has to be the 0 ring, right? So that's why, certainly if you're playing with domains, you almost always wanted 0 to not be in there, because yes, you can do the localization, but it turns out to be just a big flat tire. It's just the 0 ring, right? Okay. So let me make a couple of notes for domains. Let's see, actually, let's work through it. I guess I'm kind of dying to do this. So this will, and then I'll go back to domains for a minute. On your next homework after this one, I'm gonna give you something that's kind of fun to play around with this, but, so let's look at it. So of localization. Okay, this thing has two prime ideals. Pedro, give me a prime ideal here. Pick one.
Generated by 2.
Okay, let's do that, okay? So let's let S let me also sort of I'll contrast this. Let S be a set of elements that are not in it. Okay? If there's anything to what we've done before, there should be a saturated multiple set. So everything in Z6 that's not this, I guess, is 1 bar, 3 bar, and 5 bar. Right, okay with them? It's pretty easy to see that this is and you know what? This set actually has a 0 divisor in it, right? But lucky us, the complement, the thing that you gotta multiply this by to get a 0 divisor ain't in there. Yay for us, right? Because there's no way that you can multiply these denominators and get a 0 out of this. These two things are actually units in the ring, in the original ring, and this one's this crazy asymptote. You keep taking powers of it and it's itself, right? So, what does R localize at S look like?
The only new thing that we have is 1/3, right?
What's that mean?
The only new thing that we have is 1/3 because 1/5 was already 5 and 1/1 is 1.
Okay, so, right, so listen, okay, I like that. Let's go through kind of the equivalence classes. So what we need to do is we need to look at R over S with R in R and S in the set 1 through 5. Right? But notice, as Pedro points out, the 1 and the 5 don't make too much of a difference, right? Because this is 1 and this is -1, and so this should essentially be this. How many equivalence classes, how many distinct equivalence classes do we get?
I don't know if 2/3 is the same as 4/3, I don't know.
Well, let's see. Uh, I bet that's one of them, right? And forgive me for not using the bars anymore, but I'm lazy. I bet that's not, oh, so here's the question though, I mean, is this something new? I mean, it occurs to me that 1/1 might be 0/1, is it? Are these two equivalent? Okay, there would have to be, so let me make a, I'll do this, this will be kind of my computation board, if you will. 0/1 equals 1/1, means there exists S double prime in S such that S double prime times 0 minus 1, 0. But that would mean that 0 would have to be in that set, which is not true. So these are honestly two different equivalence classes, right? Okay. What else?
1/3.
Okay. That's 1/1.
Yeah.
Note, however, 1/3 equals 1/1. So to see this, let S double prime be 2, right? I'm sorry, not 2. It's not going to be 3. That's what I'm going to say. Notice that 3 times 1 minus 3 is 3 times -2, which is 0. Also note notice the same thing here, right? Because 5 minus 1 is 4, and 4 times 3 is 0, right? Huh. What about something like 2/1?
Pretty sure that's
Right. Again, take the 3, because 3 times 2 is 0. So actually, there are only 2 equivalence classes. And you can see they're namely 0/1 and 1/1. And this is a ring, because notice 1/1, notice 1/1 times itself is 1/1, agree?
Yeah.
What happens when you add it to itself? You get 2/1, which is the zero class. So notice in this case, actually, Z6 localized at S is isomorphic to Z2. Which is isomorphic to Z6 mod. So localization at the complement of this prime ideal is equivalent to modding out by it.
That was luck or that happened with?
That was luck,
Okay,
because this
okay.
is a von Neumann regular ring. And we're gonna see what, this is always true for von Neumann regular ring. When you mod out by a prime, it's the same thing as localizing, which is totally weird. I mean, anybody that's ever worked with domains, this is like totally too weird for color TV. Because, for example, Z localized at the ideal generated by 2 is big, right? It's N over M, where M is odd. So when you localize, so you turn the complement of the ideal generated by 2 into units, you're allowing all odd denominators. On the other hand, Z mod 2Z is not only is it not big, it's finite, and it's a characteristic too. So not only are these not isomorphic like they were here, you even change the freaking characteristic, right? So it's very, very different. So weird things can happen in localizations. I think that's kind of a worthwhile example to consider. Let me give you another quick example here. Example, suppose R is a domain. The quotient field K. And remember, the quotient field is just, all possible fractions, so you're allowing all denominators except for 0. Is a multiplicative set such that 0 is not an S. I'm going to be specific about that one here. Then RS is what we call over of R. And that terminology, I think I'll put it on one of your homeworks, but just so we're all on the same page, an overring for a domain is any ring that sits between the ring itself and its quotient. So it's a bigger ring. Overring just describes the fact that it sits inside the quotient field. Now, so what we pointed out in this example is if I walk up to you on the street and I give you a multiplicative set in a domain, and you look at RS, then that's an overring, right? So any localization in this situation is an overring. You know what's coming next. Is it true that every overring is a localization? The answer is yes for a PID, but you don't have to get too far away from a PID to find some dramatic examples of things, overrings that are not. By the way, that's a PID, isn't it? Look at me, I'm just gonna put on one more variable. Anybody give me an example of an overring of R that is not a localization? Oh, there's many of them, actually.
we localize with respect to the generated by X and Y?
What's that now?
What if we localize with respect to generated by X and Y?
But I mean, aren't you localizing?
Huh?
So I'm sorry, run that by me again?
What happens if we localize, with respect to primary deal generated by X and Y?
Right. Oh, generated by both X and Y?
Yeah.
You localize it there? Well, that'll be a localization, and what will happen is, this has infinitely many maximal ideals, but when you do your localization, it'll kill them all except for that one that you localize. But let me give you one that, an overring that's not a localization. Actually, I don't even think I have to keep going forever. I could have stopped at Y over X. But I do have a flair for the dramatic. And I also like to do this example because this example is not even, this is an overring. This kills two birds with one stone. This is an overring of a two-dimensional unique factorization domain that is neither a localization nor is it a theory. So anyway, you might think about that. Why is it the case that, there are ideals that are not finitely generated, and why is it the case that this is not an overring of the original R? Okay, any questions on that? All right, well, I will see you all on